Hello, this is Jack Jackson. In this video, we're going to talk about the derivative of the sine function. So before we formally prove the derivative formula and derive it for the sine function, let's examine the graph of y equals sine x, which is graphed here in this window on a square scale. And let's kind of review some of its properties. And then let's see if we can kind of figure out what the derivative should look like just based on what we see here. Okay, well, let's see. To start with, we got some interesting characteristics. This is a periodic function, so it keeps repeating the same pattern over and over again. The period is 2 pi, so if you go from 0 to 2 pi, you get one complete cycle. And then from 2 pi to 4 pi repeats the same y values in the same order again. And then from 4 pi to 6 pi, and also from negative 2 pi to 0, and so forth. So the same pattern keeps repeating over and over again. So notice that it hits the axis at the inflection points of 0, pi, 2 pi, 3 pi, negative pi. In other words, the integer multiples of pi. It has several maxima, which are both global and local maxima. They occur at pi over 2 plus shifts to that by 2 pi. So pi over 2 and then pi over 2 plus 2 pi is over here, which is 5 pi over 2. And then there's another one here, and there's one over here, and one over here, for example. It hits a minimum here at 3 pi over 2, or at minus pi over 2, plus multiples of integer multiples of 2 pi. So here's minus pi over 2. Minus pi over 2 plus 2 pi is 3 pi over 2. Add another 2 pi, you're over here, which is 7 pi over 2, and so forth. Notice between the minima and maxima, successive ones, the function increasing, and then it decreases down and back up and back down. And it so happens that where it crosses the x-axis, which are integer multiples of pi, are in fact the inflection points as well. Alright, so those are some characteristics of that particular graph. Now, what does the graph of the derivative look like? See if you can think about that for just a minute. And let's see if we can do something about maybe figuring out some things about where the derivative would be. Well, first of all, where is the derivative equal to 0? Well, any place that the original function has a horizontal tangent line, like at a maximum or minimum, the derivative would be 0. So the derivative is 0 at all of these places here, which turns out to be, what is it? That's the halfway in between a multiple of pi. So at pi over 2, 3 pi over 2, 5 pi over 2, odd multiples of pi over 2, and so forth. Now, notice that let's say between negative pi over 2 and pi over 2, the function is increasing, so the derivative is going to be positive, and it reaches an inflection point right here at 0, 0. Now we might zoom in here close, but I think it's not too big of a stretch to see that the derivative right there should be about 1. And so it actually is going to max out, the derivative is going to max out at about 1 there, actually exactly a 1, whenever this is 0. Now, after this maximum and this minimum, between this maximum and minimum, the derivative is negative because the original function is decreasing. And it's going to decrease down, continue to decrease here. So the derivative is negative this whole way. And it gets its lowest right here where the original one hits the axis, because that's an inflection point too. So what's going to happen is this is going to kind of come up, back down, back up. Okay. Let's see if we can get it on get this on your calculator. Okay. So try to take your calculator now and use your calculator to graph it. Remember how we've talked about how you can use the calculator to graph the derivative, at least graph a symmetric difference quotient, which is close to the derivative? Okay. Well, here we go with the calculator. You let y be y1, say, be sine of x. Let y2 be the numerical derivative of y1, which is the symmetric difference quotient. And so the darker one I have here is the sine, and the lighter one is its derivative. Here's a graph of it in Graphmatica. So the blue one is the original function, y equals sine of x. The red one is the derivative. Does that look like a function you know? That function should be fairly familiar, does it? Well, it looks like the cosine function, doesn't it? So if this is right, the derivative of sine should be cosine. We could check that by letting y3 be cosine of x and check the tables for y2 and y3, and we see that they do in fact match. So it appears that the derivative of sine x is cosine x. Now, let's actually prove that. Okay, so we're going to need a couple of identities. The first thing we're going to need is we're going to need the fact that sine of x plus h is sine x times cosine h plus cosine x times sine of h. Now, if you want to see a proof of that, then I direct you to my trigonometry videos, and we talk about different sum identities. And we're going to need that. We're going to do some algebraic things like regrouping and factoring and breaking into fractions, and we're going to use some limit properties to break into two limits. But then we're also going to be looking at these two special limits, and these are the ones that we just proved in a recent video. The limit as h goes to 0, sine h over h is 1, and then we're also going to use the limit as h goes to 0, cosine h minus 1 over h is 0. Alright, so here are the details. The derivative of sine x is the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. And what we're going to do is we're going to take this sine of x plus h and apply this identity here. So that's going to be sine of x plus h is now going to be replaced by sine of x times cosine h plus cosine of x times sine of x, h. And then we still have our minus sine x, we're still over h, and we still got our limit. Bring down our equal sign, so get all that. Now the trick here is to group it in the right way. We want the cosine x and the sine h to be put over here by itself. We'll put the minus sine x with this part here, with the first term. So we're going to group the terms 2 and 1. The first and last of the original are grouped together, and then we have the middle one over here by itself. Both of these have a sine x, which I can factor out of this binomial. So I have the limit as h goes to 0 of sine of x times cosine of h minus 1 plus cosine of x times sine of h over h. Since it's all over h, I could also break it into two fractions. So this is sort of like just getting our common denominator, put them together, just kind of reversed. Now, provided both of these limits exist, then separately, the limit of the sum is the sum of the two limits, and since the sine of x has nothing to do with h, it's a constant in terms of h, the sine of x can be brought out front of the limit sign, and similarly the cosine can be brought out of the front of this limit sign. So sine of x doesn't have any h's in it, so it goes out front of the limit sign. Similarly for cosine x in the second part. So we have sine of x times the limit as h goes to 0 of cosine h minus 1 over h, plus cosine of x times the limit as h goes to 0 of sine of h over h. Now you see why we need those two limits. This limit on the far right is 1, excuse me. The one here on the left is 0. Sine of x times 0 is 0, plus cosine of x times 1 is cosine of x. And sure enough, the derivative of sine x is cosine x. And there's another picture of it. Pretty cool, huh? Alright. We'll derive the formula for the derivative of cosine x in the next